All right, in this video, we're going to begin Calculus 2, or integral calculus. The first four chapters of the textbook, well, not the opening chapter, this was like a pre-calculus, so chapters 2, 3, and 4 are what is taught in Calculus 1, or differential calculus, the meaning of the derivative, the differentiation rules, and then some of the fundamental applications of differentiation are what is taught in Calculus 1. But now in Calculus 1, we also learned about limits. So, what exactly limits are and how to evaluate them. And so in Calculus 2, even though limits are a part of Calculus 2, limits are a foundational part of all of calculus. But in Calculus 2, we aren't going to have to relearn limits. In addition to integration, there are some extra topics that we're going to learn. So chapters 5 through 8 are all about integration. Chapter 9, differential equations, we're going to skip in this course. This chapter is just a basic introduction to differential equations, but there's going to be a full course, a full separate playlist all about differential equations. So we're not going to go through chapter 9 here in Calculus 2. But Calculus 2 also includes Chapter 10 here on parametric equations and polar coordinates. And then also in Calculus 2, we go through Chapter 11 on infinite sequences and series. And then Chapter 12 and on are Calculus 3, multivariable calculus. But Calculus 2, I would say that in general, the general consensus is that Calculus 2 is a bit harder than Calculus 1. I mean, because first of all, we've got 4 chapters you can see on integration, whereas in Calculus 1, we just had a little more than 2 chapters on differentiation, chapters 3 and 4, and then just the end of chapter 2, because chapter 2 was mostly about limits. But here, again, we've got 4 total chapters on integration. Chapter 10 isn't so difficult, but chapter 11 is its own separate full topic. Infinite sequences and series. So there's a lot to cover in Calculus 2. But then in addition to that, I would also personally say, and I think most people agree, that integration is a little more difficult to grasp than differentiation. So Calculus 2 is challenging, but if you just systematically make your way through it, work plenty of example problems, then you'll be fine. Okay, so we're going to start in Calculus 2 with an introduction to integration. In this video, we're going to go through the opening section of chapter 5, or if the video runs too long, I might split this opening section into 2 separate videos. Now, but what's interesting, though, is the term integration, or integral, or integrate, is not stated once in this opening section. You don't officially see the term integral, not just in this opening section, but in any of the previous sections in chapter 4, 3, 2, or 1. You don't ever officially see the term integral until the start of this section 2, section 5.2. And so in order for you to really grasp probably the most important topic in all of calculus, which is what we talk about in section 5.3, the fundamental theorem of calculus, it's important that we have a solid understanding of the term integrate or integral. How exactly is this term used? How exactly does this term fit into everything we're doing in calculus? So if we come back to the end of Calculus 1, the last section of Calculus 1, if you remember, was where we talked about antiderivatives, the idea of anti-differentiation. So coming into section 4.9, we had learned all about differentiation, the meaning of the derivative, the differentiation rules, applications of differentiation. And so to close out Calculus 1, differential calculus, the last thing we wanted to talk about was we wanted to think about the idea of going in the reverse of differentiation. So if we have some function, f of x, well, we learned how we could take the derivative of f of x to get some new function f prime of x. But what about the idea of, so here you can think about we're going in the forward direction, finding the derivative of f of x. But what if we wanted to go in the reverse direction and find a function whose derivative is equal to f of x, some function capital F of x. So we're going in the reverse direction. In sequence, you have this function capital F of x. You take its derivative, you get f of x. You take the derivative of f of x, you get f prime of x. But we're starting with f of x here, and we want to go in the reverse direction of differentiation and find a function capital F of x whose derivative is f of x, whose derivative is the main function we're working with, right? And so since it's like we're going in the reverse of differentiation, we called this process anti-differentiation. We're finding the antiderivative of f of x. In this direction, in the forward direction, we're finding the derivative of f of x to get f prime of x. Now going in the reverse direction, we're finding the antiderivative of f of x to get capital F of x. But now, most people, when they finish calculus and move on with their studies, they completely forget about the term antiderivative. Most people call this process of going in the reverse of differentiation, that they call this integration. You're taking the integral of f of x. And in this direction, you're taking, this is differentiation. And that's not wrong. That is the correct terminology to use for this process once you're finished with calculus. But what we want to learn in this course is exactly where this term comes from. Because, so anyone that has completely forgotten about the term antiderivative, anyone that I would talk to that would act like the term antiderivative needs to be removed from the calculus dictionary because it's just an integral, well, to me, that's a clear indication that this person doesn't truly understand the fundamental theorem of calculus. So as we start calculus 2, let's sort of imagine that we were inventing calculus. So we're Newton and Leibniz, who they developed calculus independently in the late 1600s. Okay, so we started by formulating everything in differential calculus, right? So we started by formulating everything in differential calculus. And so now the last thing we're working on is, now that we understand the derivative, the last thing we're working on is we're just thinking about this idea of going in the reverse of differentiation, right? So here's differentiation. And we're just starting to think about the idea of going in the reverse of differentiation. And the name that we decide to call this process is anti-differentiation. It's a natural, simple name. That's it. So we solved the tangent line problem and the velocity problem by inventing the derivative. Then we created some very simple differentiation rules that people can use to make differentiation easy. And then we developed all kinds of interesting uses of differentiation, ways that you can apply differentiation to answer questions and solve problems that aren't just solely about, okay, what is the slope of this tangent line at this point? What does differentiation tell us about shapes of graphs and different phenomena? And so now we're moving on to dealing with the area problem and the distance problem, okay? But it's very important that we think about how coming into working on the area and distance problems, there's nothing to indicate that the solution to the tangent and velocity problem is going to have any relation to the solution to the area and distance problems, other than the fact that we plan to use limits to solve the area and distance problems, just like we used limits to solve the tangent and velocity problems. Other than that, as far as we can tell, there's not going to be any relation here between these two concepts. Now, maybe with Newton and Leibniz being geniuses, they might have had a sixth sense that there would be a relation, but just trying to go through calculus as sort of like a story, I think makes it more intuitive to learn. So, okay, the area and distance problems. Remember, in the opening video to this playlist, or it might have been the second video, we talked about how calculus can mainly be thought of as, can fundamentally be thought of as, so like the ultimate reasons we can think about why calculus was invented was to solve the tangent and velocity problems as well as the area and distance problems. The tangent and velocity problems were solved with the derivative. But now the area and distance problems are concerned with, so prior to calculus, if you were trying to find the area under this curve here, so you have this function f of x, and you want to find the area between the function curve and the x-axis from x is equal to a to x is equal to b, the area of this region S. Well, just how with the tangent problem, there was no official systematic way of finding the slope of the tangent line to a general curve at a point. Well, with the area problem, so if the function curve is not like a horizontal line or a slanted line or at least some combination of straight lines, something simple, well, in the same way, there's no official systematic way of finding an area like this. And then the distance problem is just the real world application parallel to the area problem, right? So, like the velocity problem was just viewing the tangent problem from a real life application perspective. What's like the instantaneous velocity of a particle or a vehicle or whatever at a moment in time? The answer is it's the slope of the tangent line to the corresponding position versus time curve at that time. Well, the distance problem is just viewing the area problem from the perspective of an area under a curve like this, having a real world application meaning. So if you wanted to find the distance traveled by some particle or some vehicle in some time interval, and you have the velocity versus time curve of the vehicle or particle over that time interval, well, then the distance traveled in the time interval corresponds to the area under the curve. Okay, so it says in this section, we discover that in trying to find the area under a curve or the distance traveled by a car, we end up with the same special type of limit. Yeah, the area and the distance problems both ultimately come down to finding areas under curves. Okay, so we begin by attempting to solve the area problem. So how do we find the area of the region S that lies under the curve y is equal to f of x from a to b? How do we find the area of this region S? So like it says here, we can describe this region as it's bounded by the vertical line at x is equal to a, the vertical line at x is equal to b, the horizontal x-axis, and then it's bounded at the top by the function y is equal to f of x over the interval from a to b. So where f of x, the function over this interval, is a continuous function and it's always positive. So it's not like we can't apply everything we're about to learn about integration to functions that aren't continuous over an interval or that do dip below the x-axis and above the x-axis over an interval. But at the moment, we're just trying to keep things simple here. And also at the moment, we're actually trying to think about a precise meaning, a precise rigorous definition of the concept of area. So if we're thinking about actual areas, cross-sectional areas of planar figures, then we don't want to think about, this one of the boundaries not being continuous. What does that mean? Or if one of these boundaries was dipping below the x-axis, it's like you have a two-piece area or something. So if we're thinking about the precise definition, the precise meaning of area, then we want to think about some general curve f of x, some general random arbitrarily shaped curve f of x as being one of the sides of this region. But now notice though, they did not specify that this curve here has to be differentiable, only that it's continuous. So it could potentially be the case that this upper curve has a kink in it. So we want to find the cross-sectional area of this region, bounded above by a curve that is not differentiable everywhere, but it's continuous everywhere. Okay, so now it says, in trying to solve the area problem, we have to ask ourselves, what is the meaning of the word area? This question is easy to answer for regions with straight sides. Yes, so it's not like coming into this section, we have no familiarity with areas. No, not at all. In geometry, we learn how to determine areas of shapes like rectangles, squares, triangles, polygons. But like it says here, it isn't so easy to find the area of a region that has curved sides. Okay, and so now, first of all, you might be thinking, well, what about a circle? Don't we learn the area of a circle in basic geometry? Well, this is a special case in that the area of a circle was officially defined well before calculus. The credit for the area of a circle being pi r squared is usually given to Archimedes, who lived from like 290 to 210 BCE. He was the first that is said to have rigorously proved the formula A is equal to pi r squared. But Archimedes is said to have used what's called the method of exhaustion for his proof, which is very similar to the idea of the limit. Okay, but other than a circle, like the textbook says here, if we're trying to find the area of a region that has curved sides, other than the special case of a circle, or one of the sides of the region being like the arc of a circle, then it isn't so easy. Before calculus, there was no official established simple way of doing this. Now, just to point out, you might be thinking, well, how could we find, so once we learn all of the techniques for integration, we'll be able to find the area under a curve like this. Well, how is that going to help us find, if we had a general shape that had just these non-ordinary sides all the way around? Well, in a case like this, we don't have straight lines on the side and a straight line below. Well, okay, just think about how once we learn how to solve a problem like this, first of all, you could reorient something like this however you need. If you want to treat the y-axis as the independent variable and the x-axis as the dependent variable, you can reformulate the problem to do that, which means that you can think about finding the area under a vertical curve. But then you can also flip this the other way with a curve like this. You can orient this problem however you need. So if we can understand how to use calculus, how to use limits to solve a problem like this, then you could just break a problem like this, finding the area of a shape like this, into pieces of problems like this. Okay, so it says, we all have an intuitive idea of what the area of a region is. But part of the area problem is to make this intuitive idea precise by giving an exact definition of area. So yeah, we talked about this in regards to the tangent problem, solving the tangent problem. And that we could think about how it's not like when Newton and Leibniz were inventing calculus and solving the tangent problem. It's not like what they were doing, at least the concept of what they were doing was rocket science or some mind-bending concept like Einstein inventing the theory of relativity or discovering the theory of relativity. So what I mean is, any scientist, mathematician, physicist at the time understood algebra very well. Everyone knows what a line is. Everyone understands the equations of lines, the slope of lines. Everyone has a general sense for the idea of what a tangent line to a curve at a point is. And in general, you could think about how everyone, if you asked someone at the time to give you a good estimate of the slope of a tangent line to a curve at a point, pretty much any scientist or mathematician is going to be able to give you a pretty good estimate for that slope by doing something similar to making a secant line and then just putting into their calculator smaller and smaller numbers, letting the second point of the secant line away from the point of interest approach the tangent line point. But the genius comes in, the brilliance comes in from the perspective of Newton and Leibniz inventing the system that's used to officially, mathematically, precisely put a stamp on the definition of the slope of the tangent line to a curve at a point. The fact that right now I could be given any function And if you ask me, okay, what's the derivative of this function f of x with respect to x in general? And I can say, okay, bring down the 2, multiply by 3, 2 minus 1 is 1. There you go. There's the derivative. So now I can give you the slope of the tangent line to this curve at any point x. Just plug that point x into this function. That's brilliant. The entire underlying system that allowed me to determine this derivative function that quickly and that easily is what differential calculus is all about, is what Newton and Leibniz developed is all about. And so that's what they're saying here. We all have an intuitive idea coming into Calculus 2 of what area is. Just like when Newton and Leibniz were inventing differential calculus, everyone had an intuitive idea of what a tangent line is, and what the slope of a line is, the equation of a line is, etc. But part of the area problem, part of what we're trying to do here is to make this intuitive idea of area precise, give an exact definition of area for any shape, for a shape with any kind of curved sides, whatever, not just these straight-sided polygons. Okay, so it says, recall that in defining a tangent, we first approximated the slope of the tangent line by slopes of secant lines, and then we took the limit of these approximations. Okay, so just like with the tangent problem, we're going to once again use limits to solve the area problem. And remember, so like from a physical standpoint, how the limit was used to solve the tangent problem was, so you have some general function f of x. We want to find the slope of the tangent line to f of x at point P. All we did was we picked some point Q, which could be located anywhere on f of x to the left or right of point P, just not at point P itself. So this other point Q has some arbitrary location on f of x. Okay, then we thought about how we can connect a line between point P and point Q, which is called the secant line, because it touches f of x at 2 points. It's the secant line. And the idea is to compute the slope of the tangent line to f of x at point P. You construct what's called the difference quotient, which is just this delta y here divided by delta x. And how exactly you construct the difference quotient, it doesn't matter. There's different ways you can label the x coordinates of point P and Q and the y coordinates of point P and Q, to where you can get different forms of the difference quotient. But in all cases, the slope of the tangent line to f of x at point P is just you take the limit of the difference quotient as the denominator. So the difference quotient is delta y divided by delta x. And when you take the limit as the denominator of the difference quotient approaches 0, then that is what's defined to be the exact slope of the tangent line to f of x that touches point P. And so what you're ultimately doing is you have some point of interest P that you want to find the slope of the tangent line. You're picking some arbitrary point that's not on point P, but on f of x, some arbitrary point Q. It can be located anywhere to the left or right of point P, just not on point P itself. You're constructing a secant line between point P and point Q, and then just finding the slope of that secant line as point Q approaches point P. So as Q gets infinitesimally close to point P from either side of P, what does the slope of that line between point P and point Q approach? That's, by definition, defined to be the slope of the tangent line to f of x at point P. Now, because this limit here has many different applications that aren't always strictly associated with just finding the slope of a tangent line to a curve at a point, this limit was pulled away from the specific context of the slope of a line, and this was called just the derivative of f of x at some point P. But in general, you can think about the derivative of the function f of x, just f prime of x, to where we say that the slope of a tangent line to a curve at a point corresponds to the derivative, to where in that sense we can say, okay, well, the derivative also defines other features in math. It's not just married to slopes of tangent lines. Okay, so that's the mechanics of the limiting process that was used to solve the tangent problem. So it says we pursue a similar idea for areas. We first approximate the region S by rectangles, and then we take the limit of the areas of these rectangles as we increase the number of rectangles. Okay, so the following example illustrates the procedure. So let's go through this example to get a sense for sort of the mechanics that the area limiting process is based on. So again, here were the mechanics of the secant line limit. The limit as Q approaches P. Well, what does the slope of the secant line between P and Q approach? In that case, the slope of the secant line turns into the slope of the tangent line. As we go through this example, let's try and think about the parallels to what is like the secant line in terms of area. And then when we apply the limiting process, what exactly is the tangent line in terms of area? Well, the parallel to the tangent line is going to be that once you apply the limiting process, the area is the definition of the exact area under the curve. Okay, so in this example, we want to use rectangles to estimate the area under the parabola y is equal to x squared from 0 to 1. So here's y is equal to x squared. So the area under this curve from x is equal to 0 to x is equal to 1. So we're bounded below by the x-axis, the horizontal x-axis. We're bounded on the right by the vertical line x is equal to 1. And then we could be bounded on the left potentially by the y-axis. But when x is equal to 0, y is equal to 0. So we're not bounded on the left by anything except for the origin. So we're just bounded then above by the curve y is equal to x squared. Let's start by seeing how we can use rectangles to estimate the area under this curve. And so this is like constructing the secant line. The slope of the secant line can be used as an estimate for the slope of the tangent line, right? Because if you let the x coordinate of point Q, let's say get within 0.1 of point P, 0.1 of point P, well, that's pretty close. That's going to give you a pretty good estimate of the slope of the tangent line at point P. Okay, so they start with the absolute simplest approximation by saying that, so the area S, this area S must be somewhere between 0 and 1 because S is contained in a square with side length 1. So if we say that, okay, let's just make a rectangle, in this case it's going to be a square, that has side length just equal to the entire x-axis range of the region, so that's just equal to 1, well, then the area of this square, we could call our first estimate. We know that the area S must be greater than 0. We can see there is some area here. Okay, but we also know that this area S can't be greater than the area of this square. We can see that that's definitely the case. And we know the area of the square is so 1 times 1. So our first estimate is that the area of this region A is something between 1 and 0. Okay, but like it says, we can certainly do better than this. So suppose now we divide the region S into 4 strips instead of 1 strip. So to do this, we can think about splitting up the domain interval, the input interval from 0 to 1 into 4 separate regions. And so the simplest way to do this is to just say, okay, well, take the entire length of this interval, 1, and divide it by 4. So what they do is they put a vertical line at 1/4, then at 1/2, then at 3/4. So now we've got these 4 separate intervals, which means that the area of the region is you take the area of S1 plus the area of S2 plus the area of S3 plus the area of S4. And so now the simplest way to get an approximation for the area of S1, S2, S3, and S4 is to just take the base width, which we know for each of these is 1/4, and multiply that width by some height value to where we get the area of like a vertical rectangle. And we can get a height value for each one of these intervals using the function. But to do this, we need to choose at which point within each interval, at which x point within each interval are we going to use for the height of the rectangle. So again, the height is going to be based on the function, but so like for region S3, the area of region S3, we're going to approximate as 1/4 times some height. Well, is it this height? Is it this height? Is it this height? Which x coordinate within this interval are we going to plug into the function to get the height? Well, okay, what they do first is they say, well, let's go ahead and do this using the right endpoints. So the height of each of these rectangles, each of these intervals, each of these strips is going to be based on the value of the function when you plug in the right endpoint of each interval into the function. So you plug in 3/4 into the function, and that's the height of S1. So there you go. There's S1. The height of S2 is going to be, you take the right endpoint and plug it into the function, right? This point is f of 1/2. So there's the height of the rectangle of S2. Same with S3, same with S4. And so now, when you add up S1 plus S2 plus S3 plus S4, you get a much better approximation than when we just used one rectangle, one strip. And you can note how, in this case, we did use a right endpoint method for getting this rectangle, because we could have said that we're going to break this region up into one strip. So the entire rectangle width is just one, but maybe we decided to make the height of that rectangle be the midpoint of the function. So we made an approximation for the area of S with this rectangle. So just notice again that this first approximation we did was based on a right endpoint method with one strip. Here, we're breaking up the area into 4 strips and using a right endpoint method for the height of the strips to get an approximation for the area of S, which again, it isn't the best approximation. We have a good bit of error here, but still, it's better than what we found using the single strip. Okay. So, using the right endpoint method, they go ahead and actually perform the sum. So you've got 1/4 times, and then plugging 1/4 into x squared, that's 1/16. So 1/4 times 1/16 plus 1/4 times 1/2 squared is 1/4. So plus 1/4 times 1/4, then plus 1/4 times 3/4 squared, then plus 1/4 times 1 squared. So R sub 4, they're saying you're breaking up the interval into 4 pieces, and then you're using the right endpoint method. So there's 2 variables here. You have, we could leave the right endpoint method, but instead break up the interval into 20 pieces or 30 pieces, but still use the right endpoint method. Or we could use like the left endpoint method. We could be doing L10. We'll talk about the left endpoint method in a second, where instead for the height of each strip, we're evaluating the function at the left endpoint. And then, but using 10 strips, or you could still use 4 strips, but switch this to the left endpoint method. So with the right endpoint method and 4 strips, again, you do 1/4 times 1/4 squared, or 1/16, plus 1/4 times 1/2 squared, plus 1/4 times 3/4 squared, plus 1/4 times 1 squared. And they get 15 over 32, so 0.46875. Now, but like it says here, we can visually see that for this specific case, it's clear that this is an overestimation of the actual area. Now, you might be wondering, well, will it always turn out that way if you're using right endpoints? Well, no, not necessarily. You can imagine if this function was decreasing, then the right endpoint method would be an underestimation of the actual area. But for this specific problem, it's clear that the R sub 4 is an overestimation of the actual area of S. So we know for sure that the exact area of the region is less than this 0.46875. And we actually know that it must be greater than 0 as well. So we went from a bound of the area is less than 1 and greater than 0. And after splitting up this region into 4 pieces, we've tightened that constraint to where we're above 0, but now we must be less than 0.46875. Okay, so now what they do next is they determine L sub 4. So all you're doing in this case is you've got the same strips, but now the heights are based on the function evaluated at the left endpoints. So you've got 1/4 times f of 0 is just 0, so there is no height of this rectangle. Here you've got 1/4, it's still an interval width of 1/4 times Now the height of the rectangle is 1/4 squared. So 1/4 times 1/16 plus 1/4 times 1/2 squared. And here's L sub 4. And it's clear that that L sub 4 is an underestimation of the actual area under the curve. But this is useful because now we can raise this lower bound of 0. We know that the actual area is less than 0.46875, and we know that it must be greater than 0.21875. So we have a tighter constraint on what the actual area must be. And so it's saying how we can repeat this procedure with a larger number of strips. The figure below shows what happens if we divide the region into 8 strips of equal width. So this is R sub 8. And here's L sub 8. By going through the same process, we have an even tighter constraint on the area, the actual area. So again, this is L sub 8, this is R sub 8. Okay, so now one possible answer to the question of what is the true exact area of region S, of the area under the curve of y is equal to x squared between 0 and 1, between x is equal to 0 and x is equal to 1, is that the true area S lies somewhere between these two values. And we can see the parallel to the secant line, tangent line process in that what we're doing at the moment is, so it's like we've constructed this secant line between P and Q, and we're just letting Q get closer to P. We started off by saying that Q was within 1 unit of P on either side of P, and that was an approximation for the tangent line. Then we let Q get to within 1/4 of point P on either side of P. That's a better approximation. Then within 1/8 of point P, that's a better approximation. But it's still just an approximation. And so it says we can obtain better estimates by just increasing the number of strips. If we think about how, in general, you have an L sub n and an R sub n, well, let's just keep increasing n to 10, 20, 30, 50, 100, 1,000. So when n is equal to 1,000, here's L sub n and here's R sub n. So the actual area of the region S must be something between these two numbers. And if you take the average of these two numbers, you're going to get a really good approximation for the actual area. Here's the average of these two values. And so to get an official exact area to where we can put a stamp on the value and say that here is the exact area of this region S, we need to apply a limiting process. We need to apply a limit. The limit in this case is going to be a little bit different from the tangent line limit in that with the tangent line, we're letting this delta x approach 0. Delta x is going to become infinitesimally small when the limit is applied. But with this area problem, we're going to be going in the other direction. We're going to be letting the number of strips, the number of divisions, we're going to be letting n go to not 0, but go to infinity. And when we apply this limiting process, that's when we get our quote-unquote tangent line, or in this case, the exact area under the curve. Okay, and so it looks as if we've got 0.33333. It looks as if the area, if we did like a limiting process as n goes to infinity, it looks as if the area is approaching 1/3. All right, and so to analyze this further, they start by just focusing on R sub n. So we can say that it looks as if we let n go to infinity, that it looks as if R sub n is approaching 1/3. Okay, and so that's what it says here from the values in the table in the previous example. It looks as if the R sub n is approaching 1/3 as n goes to infinity. And this is confirmed in the next example. So for the region S in the previous example, the area under the curve y is equal to x squared from 0 to 1, show that the sum of the areas of the upper approximating rectangles approaches 1/3. So we had R sub 4, R sub 8. That's the sum of the upper approximating rectangles, the right endpoint rectangles that they were upper approximating for this specific example. The sum of, but not 4 or not 8 rectangles, but n rectangles. N of these right endpoint rectangles, to where n is any positive integer. We want to show that as n goes to infinity, this R sub n goes to 1/3, approaches 1/3. And so what they do is they just write out a general expression of R sub n. So here's the first strip. All of these strips have width 1 over n because the entire width of the interval is 1. And then you divide the interval width is just that entire span divided by n. So each of these, the widths of the strips is 1 over n. But then the height is just, so based on the right endpoint, the right endpoint of the first strip is just going to be 0 plus the delta x. So the delta x is, again, it's 1 over n. So the height of the first strip is just you plug 1 over n into the function. So 1 over n times 1 over n squared. Now, the right endpoint of the second strip is just 2 times delta x. So 2 over n. So you have 1 over n, the widths are the same. Then here times 2 over n squared. Then times 3 over n squared for the third strip. So you extend this out. Generally, the general R sub n formula is just 1 over n times, then it's n over n squared. Because we can see that the numerator here is just whatever strip you're at. You're going from strip 1 to strip n. So they perform some algebra here to get this entire expression into this form. Now, they use a formula for the sum of the squares of the first n positive integers. So a formula for this piece here, and they don't show the proof of this. So the sum of the squares of the first n positive integers is given by this expression, so they can substitute this expression here. And so now here's the result, and now simplifying, you have R sub n is equal to this expression of n. So now we can take the limit as n goes to infinity of this expression, and just using the standard limit techniques, this comes out to 1/3. Now, but what's interesting is if you go through this same process with L sub n, the sum of the left endpoint rectangles, and so then you take the limit as n goes to infinity of L sub n, you also get 1/3, which is great. That's perfect. So when n doesn't go to infinity, if you have some finite value of n, if we come back here, so when n is equal to, so, for any of these finite values, even at 1,000, L sub n and R sub n are not the same. In this case here, they're close, but they're not the same. But in the limit as n goes to infinity, the limits of L sub n and R sub n match. So it says that because if we go ahead and do a simple visual exercise, make a graphical illustration here of, so you've got the right endpoint rectangles in figure 8 here, and the left endpoint rectangles in figure 9. If we let the number of rectangles get bigger and bigger and bigger, as big as we can let them get until visually our eyes can't resolve the rectangles anymore, it visually appears to be the case that the result is converging on exactly what we're looking for, right? For both the right endpoint and the left endpoint strips, the right endpoint and the left endpoint rectangles, it appears visually that as the number of rectangles gets larger, the result of the total areas of all the rectangles is converging onto exactly what we're trying to determine, the exact area under this curve. And this is an important step here as we progress through the process of integration. When you set up an integral and you're trying to validate that the integral you set up is correct per what you're trying to do, it's good practice to try and set up some sort of a graphical illustration or some sort of an illustration, whether it be graphical or non-graphical, that clearly indicates that as you apply the integral, as you let the number of pieces that you've defined your problem be divided up into get bigger and bigger and bigger, that the result is converging on what you're trying to determine. In some cases, when you set up a problem, you might think that it's set up correctly. The way you're dividing up the problem into pieces is set up correctly, but when you go ahead and increase those numbers of pieces, you do that illustration, it's clear that no, this is not converging to the final result like I thought it would. It needs to be very clear that this is very clear that as the number of rectangles increases, the result is converging towards exactly what we're looking for. Okay, and so with that then, it says, therefore, we define. This is a definition. So we define the area A, the area of, again, right now we're just talking about the area under the curve y is equal to x squared from 0 to 1. So we are defining that the exact area under this curve, by definition, is equal to 1/3 based on the fact that the limit as n approaches infinity of the r sub n is equal to the limit as n approaches infinity of the L sub n. They've sandwiched the ultimate area of this region to be 1/3. Okay, so great. We've started off in an effort to solve the area problem by using a limiting process, using limits to come up with a very intuitive, practical definition for the exact area under this curve, y is equal to x squared from 0 to 1, which is very important because this area has as one of its sides this non-standard curve here. That's not even the arc of a circle, which that's what the area problem is all about, right? So what we're going to do in the next video is we want to extend everything we did here in this opening example to more general cases.